Okay, so we have this report in Revit. Remember that we are working with the heating option, and here we have the conditions that Revit has used. Here we have the dry bulb temperature, negative 5.6 Fahrenheit. Okay, so it makes sense that if we are using or we are calculating the heating loads, it has to be on the coldest day. So according to Revit, the coldest day or the coldest moment, it's not a day, it's a moment, we have negative 5.6 Fahrenheit. Can this happen in King? It can happen, yes. So this is something we can do here. So if we are dealing with the outdoor temperature, here we can type negative 5.6. Okay. What's the in Revit here? We have information about the relative humidity. This is a weird units, pounds per pound. Let's say that this is 60%. Okay, so the relative humidity, the worst relative humidity that we can have is 60%. The outdoor relative humidity, 60%. Okay. And here we have information about the wet bulb temperature. Do you remember how we calculated wet bulb temperatures?
Yeah, it's thermometer with the wet cloth, with a damp cloth.
Yes. Yeah, that's the theory. We have a thermometer with a damp cloth around it. But was there a tool to calculate that? It's the psychrometric chart online. So we use this tool. It was the online, this one. Okay, so we have done this both in building science 1 and then in systems. Okay, so with this, remember that we have to set the units, English units, then reset values, submit. And now, for example, here, if the dry bulb temperature is negative 5.6, and the relative humidity, the percentage is 60%. We click here, input data for air properties, submit, and the wet bulb temperature is -6. Okay, in this case, in Revit, is -5.6. It's not a big deal, but again, we have this tool. When look at this, this chart is only as of 20 Fahrenheit. When we have very cold temperatures, are getting that we can assume that if the temperature is below 20, the dry bulb and the wet bulb temperature are very similar. Okay, so that's why Revit has considered that the wet bulb temperature is the same as the dry bulb temperature. I'm sure that it doesn't happen in summer. So let's select the cooling. Okay, so for the cooling system, we have 80 Fahrenheit, the dry bulb temperature, 87, and the wet bulb temperature is 69. If we go to this chart and the dry bulb temperature is 87, we calculate it again. The wet bulb is 75. Probably it's because of the relative humidity. Let me check. Yeah. Okay, so if we have 87 dry bulb temperature and the relative humidity is 50%, the wet bulb it's 72. In Revit is 69. Okay, we're getting there. The problem is that I don't know these units. The relative humidity is not in Revit. I don't know why. It's not given in percentage. So we have these units. So somehow we have to turn these units into percentage. We're not doing it, okay? Anyway, you see that this is complicated. We have different tools depending on the units. We can have, but we have different tools to calculate all this and to check whether what we are doing is right or wrong. If the wet bulb temperature here is 72 and REVIT is considering 69, okay, that's fine. The problem is that we are considering 69 in REVIT and 20 in the other tool. Then there's a mistake. But if there is only 1, 2, 3 Fahrenheit difference, it's fine. Anyway, these are the conditions. So we have the outdoor conditions, negative 5.6, relative humidity 60. And then we have the indoor conditions. Do we have indoor conditions for REVIT? I think we have set the, so we have set the conditions here. So this is outside and this is the zone, okay? It's 75. It's 75 for cooling, but we are working with heating. Okay, for heating is 70 and the relative humidity, no, this is the humidity ratio. Now I get the point. Okay, so this is the relative humidity and this is the humidity ratio. So that's why we have these units. Okay, now I get the point. But you can see that inside in the zone or in the space, the dry bulb temperature is 70 and the relative humidity is 27.4. It's low, a little low in my opinion. So here we have the indoor temperature 70 and the relative humidity is 27. Okay, 27 relative humidity is a little dry. Okay, so it's not perfect comfort, but well, those are the conditions that we have here. 70, the dry bulb temperature, 27, relative humidity. So when we have the same conditions, kind of, we have the same conditions here, then things change, especially what affects the condensation change. You remember that the colder the outdoor temperature, the more likely we will have condensation here. If this outdoor temperature is 20 Fahrenheit, probably there won't be any yet. So at 20 Fahrenheit, we don't have condensation. At negative 5.6, we do have condensation risks. Okay. What can we do to prevent this from happening? The condensation. What can we do?
Vapor barrier.
Vapor barrier. Okay. So vapor barrier where? Inside the thermal insulation. So if this is the cellulose, this is inside, this is the cellulose. We have to add, I'm not going to do it, but if we add, well, first we have to, okay, let's do it. So here, because the exercise was, I don't know. Like this, heating loads and condensation. So this is wall, roof, and floor. Okay, so let's do it. So inside we have gypsum board, 1 inch. So inside, let's do this, gypsum. The width is 1 inch. The thermal conductivity of gypsum is 0.98. Here the thermal conductivity is 0.98. Then just in case, I'm going to apply this vapor barrier here. So the vapor barrier, the thermal conductivity is whatever, it doesn't matter, and the thickness, it's something extremely thin. So let's work with something 0.1. 0.01, sorry. Okay, something very thin because it's a membrane. And then what else we have? Air chamber, a 2-inch. No, we are working with the gypsum board. Okay, so we have a 2-inch air chamber here. So here, after the vapor barrier, we have air. And what's thermal conductivity of air? 0.9. And the width, it was 2 inches. Okay. Then the next layer is the glass wool. And here we don't have any, well, we want, so this is what we want. The R value of the wall has to be more than 40. So you have to calculate the thickness or the width of this glass wool. So first, here we have glass wool. Then we have to check the thermal conductivity of glass wool. Where is it? Glass wool insulation, 0.23. Glass wool, thermal conductivity, 0.23. The thickness, well, with this thickness, with 5 inches. So let's complete the detail, and then we will find out the width of this. Okay, so we have glass wool. Then the next layer is the air gap, 2 inches. Okay, so we have another air gap. The thermal conductivity of the air gap is 0.9, and we have 2 inches, same here. And then the last layer is 4 inches of brick. Okay, so we can type here brick. The width is 4 inches, and the thermal conductivity of the brickwork common is 3.47. Thermal conductivity 3.47. Okay, so now we have this wall. It's from inside to outside. We have 1 inch of gypsum, 2 inches of air. We have to find out how many inches we need of glass wool, and then we have 2 inches and 4 inches air and brick. So here we have all these elements. What's the thermal? What's the R value so far? It's 30. Okay. So it has to be more than 40. So what do we have to do? We have to increase the thickness of the glass wool. 5 is not enough. Let's try 6. It's not enough. Let's try 8. Okay, with 8, it works. With 8 inches, we have an R value of 43.25. Okay. Now, the first objective to get an R value above 40. We have this, and what we have to do is to increase the thickness of the thermal insulation. Second goal, we have to prevent condensations. We haven't included any detail or any number for this vapor resistivity. Okay, so let's do it. For the gypsum, what's the vapor resistivity of gypsum? Gypsum board. Vapor resistivity is 60, is the last column here. So the vapor resistivity for gypsum is 60. I'm not going to include the vapor barrier. So imagine that this is 1. Okay, so it's not. Let's do it with the air. What's the vapor resistivity of air? Air 5.5. Okay, so let's type 5.5. What's the vapor resistivity of glass wool? Let's go to glass wool. Glass wool, it's 10. We have another air gap, so that would be 5.5. And finally, we have the brick. So what's the thermal, the vapor resistivity of brick is 50. Okay, so with this, as it was expected, we're going to have a condensation. What can we do? If we apply the vapor barrier here, if the vapor resistivity is something very high, so something with a lot of zeros, then we won't have this issue. Okay, so this is what a vapor barrier, in terms of thermal resistance, the vapor barrier doesn't matter at all. Okay, so that's why in therm, we're not simulating this, because in therm, we're not calculating condensations. In therm, we're just calculating the R value of a detail that has different materials or where there is a corner. So we're calculating this kind of R value. We're not calculating condensations. But here, if we run the first simulation without the vapor barrier, and we do have condensations, then we have to add it. I recommend you include the vapor barrier always. If you don't need it, you can type here 0. If the width is 0, then it's like you don't have this, you don't have vapor barrier. And if you need it, let's type something 0.01. It's a membrane, something very thin, and then we can solve that issue. Okay, so that's the goal of this tool. First, if we want to find out the thickness of the thermal insulation to meet the requirement that the R value is above 40, we can calculate it easily. And then we can check if under these conditions and when this weather, when outside it's below 0 Fahrenheit, condensations will happen. So having the vapor barrier, it's always something good. Okay, we can do the same thing with, there's something else we can do. If we want to evaluate, because here you see that we have the thermal load. Okay, so what's the thermal load? The thermal load is the U value. The U value is the inverse of the R value. If the R value is 43, U value is 0.02. So it's 1 divided by 43.25. Here we have the area, and here we have the difference between indoor and outdoor temperature. We have defined indoor and outdoor temperature there, and we need now the area. So where do we get the area of this element? In REVIT. If we pick the walls, well, where do we have the area of the walls? If we select the wall, we have the area of the wall somewhere. Yeah, the area of the wall is 372 square feet of that wall. If we select this wall, the area is 432. So we can add up areas, or is there a way to get the area of all the walls? Can we select all of them and get the area? No. So is there a way to find out the area of the walls? We can create a schedule. Remember the schedules? So if we create a new schedule, and in this schedule, we just analyze walls, and here we just select area. And if we click OK, what do we have? We have a schedule, and we don't have the total area, but here we have the area of all the walls. Can we rely on that? I don't think so. I don't like this schedule, so I'm going to create another one. Because here is taking into account also internal walls, and we only want the walls of the perimeter. So how can we do this? A new schedule. Here in walls, we have different options. We have wall sweeps. Okay, so let's select walls again. And here I need the area for sure. And there should be some field here about the volume, width, type. Let's select type. And what else? Assembly description. Let's select the assembly description. And we click OK. Oh, so all of them are exterior walls. Perfect. Okay. So we are not, because I didn't know that, we are not selecting interior partitions. We are selecting exterior walls. So what is the total? I would like to see the total, but I don't have it. Okay, but I have to add up. Calculator. It's 372 plus 432 plus 360 plus 612 624 172 172 172. Okay, so this is the wall area 2,916. So if I type here 2,916, I have the wall area, and that would be the maximum heating load that we have through the wall. Okay, so I have calculated the R value, and then I just need the total wall area, and I have this number. We can do the same thing with the roof, and we can do the same thing with the floor. So let's do it. We are working with the roof. Inside, we have 1 inch of gypsum board. So we're working with the roof. Inside, we have gypsum. It's 1 inch gypsum. 1 inch. The thermal conductivity of gypsum was 0.98. And the resistivity is 60. Okay. Then next layer is 3 inches of air. So we have the second layer is air. It's 3 inches. And what's the thermal conductivity of the air gap is 0.9 and 5.5. Okay, so the air is 0.9 and the vapor resistivity 5.5. Then next layer is glass wool. Again, we have the glass wool here. How many inches? We don't know yet. The thermal conductivity is 0.23 and the vapor resistivity 10, 0.23 and 10. So glass wool is 0.23 and 10. And what's next? Oh, I did something wrong and you didn't tell me. Inside the glass wool, I think it's good if we can copy this. So here we should type always the vapor barrier. The vapor barrier thermal conductivity doesn't matter. This is 0.01. And then we will check if we need the vapor barrier or not. So we have the gypsum, air, vapor barrier, glass wool. And here we have the asphalt, 1 inch of asphalt. So this is asphalt, 1 inch. And what's the thermal conductivity of aluminum, asbestos, asphalt? 4.33, and the vapor resistivity 100. So this is 4.33, and the vapor resistivity 100. Okay. We do have condensations, so I'm afraid that we need the vapor barrier. So if we type here something with a lot of zeros, we will, even with a vapor barrier, we can have problems here. If we add more zeros, you won't have these issues. But that's gonna be difficult. Okay, so probably if we had this somewhere else, I don't know. But anyway, we need the vapor resistivity, but you see, if we add like 4 zeros and it doesn't work, things are getting serious, okay? Because that means that we need to study this case, because probably even with a good vapor barrier, we will have problems with condensation. With this crazy outdoor temperature, it's almost impossible not having condensations. Anyway, so we can do this. And what about the roof area? The roof area is easier because on the 3D model, we just have to select the roof, and the roof is 1911. So it's 1911. So that's the square footage. And here we have the thermal loads through the roof. Okay. And finally, oh, no, sorry. This is, I have to change the R value. So what is the requirement for the R value? The roof has to be more than 55, okay? So now we have to select another thickness for the glass wool. Let's say 10. With 10, this is 48, it's not enough. 12. It's 57, okay. So with 12 inches of glass wool, this is more than 55. Okay. And finally, we have to do the same thing with the floor. The floor is not, most of the heat goes through the walls and especially through the roof. Okay, so that's why the R value of the roof, because the heat tends to go up. So most of the heat flow will go through the roof. So the floor, it doesn't have to be, the R value has to be more than 20. Okay, makes sense, but we don't need as much thermal insulation as we need in the roof. So let's do it here. And usually we don't have those kind of condensation issues. Well, the floor is different. If there's a building and there's a roof, walls and windows, and then the floor. So now it depends on what kind of floor we have. I told you that there are exterior floors. I explained that last time. We have an exterior floor. We have an interior floor that separates a room from something that it doesn't have a heating system. And then we have the slab. The slab is something that it's just resting on the soil. Okay. So if this is the temperature here is negative 0.6 Fahrenheit. The temperature of the floor is not negative 5. It can be 30 Fahrenheit, something like that. Okay. So that's why working with floors, it's not very accurate because we are demanding an R value only of 20 first, because the heat tends to go up. And second, because the floor temperature is not as low as the outdoor air temperature. Okay, so that's why floors are not, sometimes we don't even have insulation in the floor. I don't recommend that. So I recommend always this value for the floor, because some of the heat we are losing through the floor, but it's, we lose much more heat through the roof or through the windows than through the floor. Okay, so that's probably in this Excel file, we can have different outdoor temperatures for different details. Okay, but if we are analyzing the floor, we don't have the same temperature here than for the wall or for the roof. Let's try to find out to see what happens. So you have the floor, the layers. It's hardwood, 1 inch. Then we have glass wool and concrete. So it's hardwood, 1 inch. Where's the floor? Here. We're talking about inside hardwood, 1 inch. What's the thermal conductivity of hardwood? Hardwood, 0.92. And the other one is 60. Okay. So it's 0.92, but it was 0.93 here, and 60. I think it's the same. Then thermal insulation, glass wool. We don't know the width yet, and for the glass wool, thermal conductivity is 0.23. Vapor resistivity, where is it? 10. And finally, we have concrete. Concrete, the thermal conductivity is 4.1 and 50. 4.1, 50. And what was the thickness of concrete? I don't remember. Concrete 12 inches, 1 foot. Okay. With these conditions, I haven't, well, this is 0, 0. If you have more layers, make sure that the width is always 0 and it won't affect. So we might have a condensation that we are taking into account that the outdoor temperature of this floor is negative 5.6, and usually it doesn't happen. Okay, so if the temperature were just 20 Fahrenheit, we wouldn't have condensation issues in the floor. Okay, so we can leave this that way. And if this is not dramatic, we can take for granted that we won't have condensation issues in the floor, because all the heat and all the vapor tends to go up always. It hardly ever goes down. So that's it. And what's the R value? Okay, it's 7. It has to be 20. So for the glass wool, let's try 5 inches. With 5 inches, even with 4 would be enough. Yeah, 4 inches, it would be enough. 4 inches of glass wool We have more than 20. We have more condensation risks. The thinner the thermal insulation, the more the condensation risk. Okay, so yeah, I'm not going to do it, but you should add a vapor barrier here. It's very cheap and it saves a lot of future issues. Okay, so add the vapor barrier here, and that's it. So what would be the answer to that? Well, these were the conditions. So now we are comparing this with REVIT. In your exercise, the indoor temperature should have been 70, the outdoor temperature 0. And here you have areas over the roof, areas of the walls, areas of the windows, and all that stuff. Okay. We are comparing the values with REVIT. So let's compare it. Let's open the analysis report. And through the roof in heating, we had this negative 1,000. And what do we have here in this tool? It's 2,000. Okay, so through the roof, oh, because we are, yeah, through the roof, we have 2,000 BTU hour. In REVIT, we have 1,000. What about the walls? Through the walls, we have 3,500, and here is 5,000. And what about the floor? We have the slab. Look at the slab, it's even positive. Okay, so at this moment in REVIT, it's not taking into account that we are losing heat through the floor in summer, because at this moment we are not losing heat through the floor. So here we have two different results. For the roof, here we have 1,000 and here we have 2,000. Through the walls in REVIT, we have where's the wall? Here, 3,500, and in this Excel file we have 5,000. So clearly, the Excel file is more conservative than the REVIT file. So what would we do?
Would you have to change the edit type properties of the walls and the roof in REVIT?
This is something that we haven't checked, and we have to check that. Okay, because in REVIT, what are the R values in REVIT? Let's find out. So here, I select the roof, I edit type, and what's the R value in REVIT? It's 66. And what about the roof R value in the Excel file? It's 57. Okay, so that's a reason. We have to check that. We have less thermal loads in REVIT because the R value is different. So with this detail was 57. In REVIT was, because here we have 1 inch and 1 foot and 3 inches. Okay, so let's try to get here like 50 something. Let's try with 1 foot in REVIT. And now the R value is 53. And here it was 57. Okay, so we need 1 more inch in REVIT. Edit type. So this glass wool can be 1 and 1. Now it's 58 and the other one is 57. Okay, that's fine. What about the walls? For this wall type, I edit type, and the R value, well, this R value is just 13. It's very low because, well, I have 3. Let's change this detail to glass wool. Glass wool. Okay. Now the R value is 44, and it should be 44. It's fine because it's what we have in the Excel file. In the Excel file, the R value is 43. Okay, perfect. And then what about the floor? If I select the floor and I edit type, then the R value, we don't have any R value because we haven't defined the floor. So let's select here concrete. Concrete cast in place. I think it was 1 foot. Then we have to insert another layer. This was glass wool. What was the thickness of the floor? Glass wool, 4 inches. And then we had 1 inch of hardwood. Okay. So this is 4 inches. And then inside we have hardwood. We don't have hardwood. We have oak. Let's select oak flooring and 1 inch. Because as far as I remember, here in this list of materials, hardwood it's oak, maple. Okay, so oak is the same as hardwood. So what do we have to do now? We have to run another analysis because we have changed the materials. Okay, so we run the first analysis without checking the wall properties, but now it has changed. So let's do it again. We don't have to change the spaces, but we have changed the layers, we have changed the properties of the material itself. So we have to change the energy model. So that's what I meant. We have to go to analyze. We have to delete this energy model because we have changed things. And now we have to create another energy model. We have created another energy model, and now we have to run another system analysis. So let's run this system analysis, annual, run, and we have to wait for a few seconds. Okay, so we have the new report, we have loads, we have to analyze the lobby, and then we have to analyze the heating. And now the roof is 15. The wall is 1,000, and the slab is 200. Okay, so now the wall is 1,843. And in the Excel tool, it was the wall, it was 5,000. It still works. Why is that happening? We don't know, but that's interesting because now by the way, we have reduced the thermal load. It was 19,000. Now it's 9,000. Okay, so what we are doing is improving the model. So at the beginning, with this report, the first analysis report, it was 19. The second analysis report, the heating, it was 16. Okay, and now with my new analysis report is 9,000. So we're getting better. So that's what we have. We can be sure that we are getting better. We have improved, and it makes sense because for the from the first and the second analysis, what did we do? We reduced the area of windows, so that improves the energy efficiency. For the second to the third analysis, what have I done? I have increased the R value of walls and floors. That's fine. But if I look at these two softwares,
Could be the conditions. Okay.
let's look at the conditions. They have changed. Yes. So you're I know, can you come here and yes, conditions have changed because Revit is analyzing a lot of days. Revit is analyzing well, a lot of days, 365 days, and each second is being analyzed by Revit. So the worst conditions now have changed. It's not, we had a negative 5.6 Fahrenheit. Now it's not that way anymore. The outer conditions are 31.8 Fahrenheit. Why? Because probably it was a sunny day that it's very cold, and that happens in King. Usually the coldest days are sunny. It happens. Well, if we change the conditions of the envelope, probably the worst day is not a sunny day. It's a cloudy day that is slightly warmer. And we are analyzing this in Revit with one schedule. We are not taking into account probably 3 a.m. because our schedule here, it's an office schedule. So we start at 8 a.m. and we finish at 8 p.m. Okay. So usually the coldest temperature is not at during the day, it's during the night. Okay, so we have changed the conditions and we have to keep that in mind for to analyze this. So now the dry bulb temperature outside, inside it hasn't changed. Well, the relative humidity is slightly bigger. It was 29, now it's 33, but it doesn't affect. But what affects is the dry bulb temperature. Now at this condition is 31.8. So let's change this. Outdoor temperature is 31.8. 32. Okay. So now the thermal load through the walls is 2,900, and here in Revit is 1,800. We're getting there. Okay, so it's not perfect, but we are getting there. But the slab is positive. So yeah, we are fixing things, we're understanding what we are doing. But now, is there another way? Is there another thing to check to make these two values match? You ran out of ideas?
I have another one.
Ah, you have another one. Okay, go.
So this is just looking at the lobby.
Yep.
So if you look at the area of the walls that are just around the lobby, that could affect it.
You're amazing. Yes, because we are analyzing the whole building with the Excel file, and we're just analyzing the lobby with the, so we either add up all the thermal loads to the wall, because here we have the lobby, we can analyze all the offices. So we either add up this, or we just take into account the wall area of the lobby. Let's do this. So if we analyze the project, what's the lobby area? So I have to open level. Okay, so for the lobby area, we have this wall. Okay, the area of this wall is 30 432. So with this calculator, we say 432 plus, where's the plus? Here. So we have only this wall, this half, and this half. Okay, so what's the area of this wall? The area of this wall is this one, is 372, but it's only half. And here we have another half. So the total area of the lobby is this wall plus this and this. Okay, so that would be 372. 72. So the area of the wall area of the lobby is 800. So the area of the walls, it's 800 here. And now what's the total? It's 700. And it should be I don't remember. It should be 1,800. Probably because we need, I have another idea, Daniel. And another idea is that here we have, remember that that was a mechanical room. So we are losing heat through the mechanical room too. Okay, so there are a lot of things. But at least, when in doubt, select the biggest number. Okay, but first analyze this. So it's not like, okay, no. This is 1200 and this is 900. Okay, I don't mind. First, analyze what we are doing and try to find what we are doing wrong. And here we have found that we were doing something wrong. Okay, we were considering the wrong area. But now how can I do this? Doing this with the Excel file is very difficult because how can I understand what's the temperature here? It's not heated, but it's not the temperature here. It's not the outdoor temperature. So what is the amount of heat that we are losing through this room? We don't know. Okay, so there are things that we can't do with the Excel file. And at this point, we have to trust REVIT, okay? Because we're not doing that. But anyway, if the REVIT figure were lower than the Excel figure, I would select the Excel figure just to be on the safe side, okay? Because I can't afford, if my client is cold and it's working with the heat pump or the boiler at full speed or whatever, and okay, I can't give more power and I'm still cold. What can I do? You're lost. Okay, so when you have two different figures, select the highest, because then you have to design your systems based on that figure. And don't be shy, just multiply by 1.5. Okay, so we are architects, we are not engineers. Buildings don't fly. If you asked with or if you talk with aerospace engineers, they have to put rockets in the moon. Okay, so everything, you cannot say, okay, double it. We are architects, we can say that. Okay, so if our boiler is 2000, or if our result is 2540 BTU hours, then we have to select a commercial boiler. We don't have commercial boilers with 2540 BTU hours. Probably there will be a boiler with 30 with 3000 BTU hour, or 5000, or 10,000. Select this one. This times 2. Don't be shy. Yeah, this would be enough, but what if someday something happens, it's extremely cold or whatever? Probably. This is too much. I can make sure that I have made a mistake, but it's not 4 times as much as, so that would be too much. And sometimes when you have an oversized boiler, it doesn't work well because it heats up things immediately, and then the boiler is constantly turning on and off, and then on and off, because we have a thermostat. Okay, so with the thermostat, with this thermostat, we have, okay, the temperature is 70. When it's more than 71, the boiler stops, and when it's less than 69, then the boiler starts again. If the boiler is oversized, that will happen, stop, start, stop, start, stop, start. And this is bad for the boiler itself. Okay, so you need, the boiler has to be running for 1 hour, 2 hours to increase the temperature, and then another 1, 2, 3 hours without working. If the boiler is on and off every 20 minutes, the boiler will last less than working like this. So first, analyze this. Imagine that we have this value in REVIT, and we have this value in Excel. Okay, select this one because it's higher. Then we have to analyze the commercial boilers that we have available. Double the size, no problem. You don't double the price. I mean, probably this boiler costs $100 more than this one. But it's difficult, and it's not, we can understand, okay, it's cold outside, probably we might be using the heating system. It's very hot outside, we might be using the cooling system. Or not. Or if there's a lot of people in one side, we have a cold day, but there are a lot of sunlight entering that room, probably in this room, even in winter, if it's full of people, full of computers, equipment, releasing heat, and we have solar gains, probably at that specific point, on a cold day, we would need the cooling system. Why? Because we are generating a lot of internal loads inside the building. So it's not something, sometimes we can't understand what's going on. So if we have a reliable software, we are experienced with that software. Okay, look at this. According to this software, on January the 31st at noon, in this office building with 100 people working in a small space, we need the cooling system. It's weird. Well, it's weird. It can happen. Because there are a lot of factors that with the Excel file, we can't, okay, we can, yeah, we can analyze whether we will have risk of condensations or not. We can calculate the R value. So there are a lot of things we can do with this. But this yearly analysis is complicated. That's useful if you have these conditions, if you have this indoor, this outdoor temperature, this indoor, this outdoor relative humidity, and you have this wall, this is your thermal load. But is this the worst scenario? No, you have to run this thousands of times throughout the year. You have to keep in mind everything that it's around the building. If you have a mechanical room that it's sharing some walls or some roofs or floors with the space that you're analyzing. So there are a lot of things to keep in mind. But at least we have two different softwares, and we can analyze things, and we can compare the results. And have I done something wrong? At the beginning, we had done something wrong with REVIT. We didn't have thermal insulation on the floor. We have a wall with a very low R value. Okay, by looking at this and then REVIT, we found out that there was something wrong. There was a mistake. Okay, let's fix the mistake. It's still, they don't match these two figures. Okay, there might be that I have more wall area in this tool. Okay, let's look at this. When we are run out of ideas, maybe that would be the explanation, that we are losing energy through this mechanical room. How much? I could run another, but anyway, there's a point at which let's trust this, and then trust, but double the system. Don't be shy, especially in single family houses. If you want to double the boiler for this building, probably it costs a lot of money. Okay, in small buildings, you can double this because it's not affecting the difference between a 3,000 BTU hour boiler and a 5,000 BTU hour boiler. It's not that much. In this building, if you double the required power for the systems, probably it will be serious. So that's why we have to rely. We can't calculate this system just when we are 22 and we have just gotten our degree. We need experience. But single family houses, small buildings, we can. Okay.